Today we're going to talk about circuits and magnetism. So here in this first image we have word known Jorg, and he's saying circuits everywhere in my computer. And we have a demonstration what a series and a parallel circuit looks like, which are the two types of circuits that we're going to go over in this video. So in the late 1799, the Italian inventor called Alessandro Volta built the world's first battery. The word voltage is in honor of him. He had the idea of making a random tube with discs of two metals, such as zinc and copper, separated from each other by cardboard soaked in brine. The brine helps speed up the reaction of electrons moving from zinc to copper. What is interesting is the idea that he had of putting these things together. Many of the discoveries made in the world can be from pure accident, or it can be from experimentations or observations. So when you observe something, when you work at an industry, or when you work, or when you're doing your everyday life at home, you may observe certain things to behave certain ways, and then that helps you think, what if I tried this and I tried that? Will it still behave the same way? Will it do something different? And lots of these discoveries were made by trying something never tried before, and which first begins with observation. You observe something. He possibly observed some current or flowing when he combined zinc with copper. He probably noticed a flux, and then he stacked them all up together, and in a solution of brine to help speed up the reaction and cause the flow of charges. So it's interesting how discoveries are made in science without us knowing really what to expect, and it's like this that most of the discoveries are made. So this is a drawing showing a simple demonstration of a chemical battery, right? In the figure above, there's a picture of how the metals look after the reaction has taken place for a while. So if you have zinc and zinc sulfate, and you have copper and copper sulfate, and you connect the zinc with copper through a wire, okay, and you separate the two parts of the solution with a porous surface, you have a direction of current flow from copper to zinc, because the direction of current is the flow of positive holes. There are no positive charges flowing. The electrons are actually flowing from zinc to the copper, but due to a mistake done by Benjamin Franklin, he proposed that electricity is a flow of positive charges. Today we know that there are no positive charges flowing. There are electrons flowing, but later in science and history, we didn't bother fixing his mistake, but rather decided to keep up with the idea that it's the flow of positive holes, which are regions in the material in the absence of electrons. So the way it works is that when you have zinc and zinc sulfate, and then you have copper and copper sulfate, the zinc atoms in the zinc metal, they are attracted by the sulfate, so they leave the zinc metal, and the electrons are left behind, and they flow through the wire. On the copper side of the battery, the copper sulfates are attracted by the copper metal, so there's a growth of copper in the copper metal, like the copper and the copper sulfate stick to the copper metal, and because of the positive charge, and this causes the flow of charges from zinc to copper and through the solution. That's why in order for you to have a flow of current, you need to have a closed circuit, which we fulfill that by creating a porous surface between the two sides of the battery allowing charges to flow. So a resistance is a measure of how much a material resists the flow of electric currents and is measured in ohms. So we're talking about batteries. We were talking earlier about Alessandro Volta, how he discovered this connection between zinc and copper, what led scientists to make the discoveries that they make, which I said earlier, it's through observation, through reasoning, and through experimentation and data collection, right? So as we have the flow of currents, we observe that there is a flow of charges. There are discharges of energy, and charges are flowing through conductive materials, right? Insulators don't allow currents to flow as easily, so conductors allow currents to flow easily. So resistance is the resistance of a material for the flow of electricity. So the more the material resists the flow, the harder it is for charges to pass through. So the units that we use are volts, which are joules per coulomb, energy per charge, current, which is coulombs per second, charge per second. So current is how many charges are passing per second. Volts is how much energy per charge. Resistance is measured in ohms, and resistance is equal to resistivity times the length of the object over the cross-sectional area. Each material in the universe has a resistivity. Using the equation above, its resistance can be found. The longer the material, the greater the resistance, since electrons need to move further. The thicker the material, the lower the resistance, since the electrons have a larger area to move into the material. So here is the equation. So if you want to find a resistance of a wire, resistance of a resistor, you got to figure out first what the resistor is made of, and then how long and how wide it is, in order for us to figure out the resistance of that particular material. Two types of circuits we're going to talk about here. Later in the next few videos, we're going to talk about combinations of series and parallel, but as of right now, we have two types of circuits, which is series with one loop and parallel with several loops. This right here is the battery. The longer line represents the positive end of the battery, and the shorter line the negative end of the battery. So here we have series and parallel. In a series circuit, voltages add to the total voltage of the battery. The voltage at each resistor add up to the total. The currents are all the same because we have a single wire connecting all resistors. And resistances add since there's only one pathway through which charges can flow. Here we have our known York saying, circuits everywhere in my computer, and then Zervina says, thanks to physics, I have a cell phone. So in parallel, voltages are the same because think about it, in parallel, the charges are spread out and ends up being the same voltage throughout the entire circuits. The currents add because you have several loops. The addition of all the currents through each loop adds up to the total current in a circuit, and total resistance is that equation 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistance 3 and so forth. So let's see how that will look like in a problem. So I'm going to use my calculator here so I can solve for this, and we got the voltage of the battery at 70 volts. We know resistances in series, they add up. So if you add up 11 plus 13 plus 11.5, you get a total resistance of 35.5 ohms, right? And then we know that the total current is the same currents through each resistor. So we're going to do 70 divided by 35.5, and we get a current of 1.97 amps. An amps is a coulomb per second, right? And you can always check your work by doing 70 divided by 1.97, and you get 35.5. So voltage is current times resistance. And power through each of the circuits is the current times the voltage. So all of these will be 1.97. All of these will be 1.97 amps. An amp is a coulomb per second. And the voltages add up to the total voltage. So the potential drop through each resistor, they add up to 0 once they make the loop. So we're going to do 1.97 times 11. So we get 21.7 volts through the first one. Then 1.97 times 13, and you get 25.6 volts through the second one. And then 1.97 times 11.5. Oops, hold on, let me try this again. Times 11.5, and we get 22.7 volts. Now, if we add up 21.7 plus 25.6 plus 22.7, we get 70 volts exactly. Now, the power through each circuit, if each of these resistors were bulbs, which one will shine brighter? It's the one with the highest power. So power is current times voltage. I stands for current, V for voltage. So 21.7 times 1.97, and we get 42.7 watts. And then 25.6 times 1.97, we get 50.4 watts. And then 22.7 times 1.97, we get 44.7 watts. And then the total power is going to be 88.4 watts. The total power, you also use the same equation. Now, we should be able to add 42.7 plus 50.4 plus 44.7 plus, and to get the total power. So 42.7. So 42.7 plus 50.4 plus 44.7, and that hold on, 42.7 plus 50.4 plus 44.7. You actually get something. Oh, I made a mistake. This is supposed to be, this is supposed to be 138 watts, and that checks. One last thing, I just realized I have to charge my computer. Where is the charge? Hold on. So, yeah. Before this thing closes, of course, it's important to do this, okay? Alright, I'm back. So now, moving on, for a parallel circuit, we know the voltages will be the same. So 5 volts is the voltage of the battery. So all of these are 5 volts and 5 volts. And then we can figure out the current by doing the voltage divided by the resistance. And we get 50 divided by 10, 0.5 amps. And then we have 5 divided by 9. We get 0.55 amps. And then 5 divided by 12.5, we get 0.4 amps. Now the total resistance is going to be 1 over, since this is parallel, going to be 1 over 10 plus 1 over 9 plus 1 over 12.5. And we get a total resistance of 3.44 ohms. Now, it's good to remember that the total resistance of a parallel circuit will always be smaller than the smallest resistor. So, if we do 5 divided by 0, 3.44, 5 divided by 3.44, we get 1.45 amps of current. And since currents add up in parallel, we're going to have the total current should add up. So let's see, 0.5 plus 0.55 plus 0.4, and we get 1.45 amps. So now let's figure out the power. So we get 2.5 watts here. So 5 times 0.55, 2.75 watts there. And then 5 times 0.4, 2.0 watts there. And then we have the total, which should add, you have 7.25 watts if we do so forth. So this should add, so 2.5 plus 2.75 plus 2.0, and we get a total current of about, total power of 74 watts. This is supposed to be, hold up, I messed up. So 2.5 plus 2.75 plus 2.0, yeah, 7.25 watts. So if resistors were bulbs, the bulb that would be the brightest here would be the second resistor. And in the first problem, the bulb that would be the brightest would be the bulb, also second resistor. Now, magnetism, right? What is magnetism? It's part of the electromagnetic wave or oscillation or fluctuation, right? You have a magnetized object. You have all the electrons perfectly aligned with their spin, generating this magnetic field from the object. Magnetic fields always point from north pole of the magnet towards the south, as you can see in the image. And magnetic field curls around the object. So now, we have to be introduced to Maxwell's equations. Maxwell's equations are able to explain all of electrodynamics. I start this with a quick summary. So here's the summary. Let us think of a simple magnet that is a dipole, never a monopole. It has a north pole and a south pole. The magnetic field points away from the north and towards the south pole. Inserting a magnet with its north side into a loop would cause the current counterclockwise. Inserting the same magnet and moving away from the loop will cause a current clockwise. That is because the nature of the horse change. In both cases, there is a change in magnetic flux. The current in the wire tries to preserve the magnetic field that was before. In a loop, a current clockwise will cause a magnetic field into the page using the right-hand rule. In the same loop, a current counterclockwise will cause a magnetic field out of the page. Inserting a magnet inside a loop with its south side will cause a current clockwise. Moving the same magnet away from the loop will cause a current counterclockwise. A change in magnetic field causes an electric field. Similarly, a change in electric field will cause a magnetic field. An electric field diverges from the source and may also curl if you have a positive and a negative. A magnetic field curls around itself and its divergence is zero, meaning the magnetic field doesn't have a single north side and a single south. It's always followed by, a north is always followed by the south, and magnetic field curls. An electric field can be monopoles, such as single negative particle, but magnetic fields are only dipoles. Here are Maxwell's equations. The first equation shows the divergence of the electric field. If you have a single charge or a charged object, the field diverges from that charge. The second equation shows the divergence of magnetic field represented with the letter B, while the electric field is represented with the letter E. The magnetic field does not diverge, so the divergence is zero because the magnetic field always curls on itself. The curl of E is equal to the change in magnetic field. So if you have a wire carrying a current there's or if you have, let's put it this way, you have a coil of wire. The coil of wire has currents passing through the coil, which is curling the electric field. That generates a magnetic field. And also the other way around, the curl of B, when B curls, you have the formation of a current. So when you insert or take away a magnet from a coil, it induces a current represented by the letter J here, and a change in electric field over time. And C here is the speed of light, and E naught here is permeability of free space. Alright, so here we have putting a magnet with the north side facing the loop current counterclockwise. Taking off the magnet with the north side facing the loop gives you a current clockwise. Putting in a magnet with the south facing the loop current clockwise. Putting out of a magnet with the south facing the loop current counterclockwise. And this follows the idea that nature of the horse changes. Alright, so now, when a current runs through a coil, it generates a magnetic field as shown. So if you imagine a coil like here, where you have the wires going like this around the cylindrical shape, the current passes through the wires, are represented by the fingers. And the thumb points in the direction of a magnetic field generated from the coil. That is using the right-hand rule. Once again, thumb in the direction of magnetic field and 4 fingers in the direction of the currents in the coil. Now, if you have a particle traveling in a region of magnetic field, it experiences a force as shown in the right-hand rule. Use your right hand, not your left. So the thumb is the direction of the current. The 4 fingers is the direction of magnetic field, and the palm faces the force that the particle will experience in that field. Now, if you have a current-carrying wire, the magnetic field will curl around the wire, and the thumb should point in the direction of the current. So these are the usefulness of the right-hand rule. Now, using the right-hand rule, we can explain the electric motor. The top portion of the loop is pulled out of the page because current is flowing in the direction of the arrows. The magnetic field points from north to south. So if you do the right-hand rule, the magnetic field points from north to south, and then the thumb is in the direction of the current, so your palm is facing you. So this portion of the electric motor coil will come out. Well, the bottom portion you flip, because this time the current is to the right, the magnetic field is still down, but this time the palm is facing the screen. So that means that portion of the loop goes in and you have rotation. But in order for you to have a complete rotation of the electric motor, there should be an alternating current here that will flip the direction of the current so you can complete one revolution. Similar things for how a speaker works. Basically, you have a magnet, and here we have an alternating current with a wire and a coil. Depending on the direction of the currents in the coil is attracted or repelled by the magnet under it, and this left and right motion vibrates the membrane in the speaker, which generates the sound and air. Once again, using the right-hand rule, you can explain both about the electric motor and about how a speaker works, and many other things are yet to come. Many other electronic devices can be explained just by the right-hand rule. Now, right here we have wires carrying current in the direction of the arrows, and the magnetic fields are the dots and the axes. Dots means the magnetic field is out of the page, or in our case, out of the screen, and axis means the magnetic field is into the page. So which way would the force exerted on the wire be? So I'm gonna select two on the well, actually might as well do all of them. So in the first case, the magnetic field is out of the page, the thumb is up and to the left, so the force is right around this way on this wire. So I can actually use, and maybe I can just copy this, and let me just paste it really quick. Yeah, so they have another one. On this one, so you're going to have magnetic field is out of the page, so you're going to have a current, a force on this wire. This way, the fact that wires experience forces is what allows us to have electric motors, speakers, and so forth. And this one will be this way, right? Notice that it's always to the right of the current. Now, so let's see this. So now we have magnetic field into the page, and the current is down and to the right. So it looks like the magnetic field will be this way. The magnetic field will be left of the current. And then we're going to have this right here. And apparently this is going to be the same right there. Okay. So that these are the arrows. The blue arrow shows the direction of the forces that the wires carrying currents in the black arrow will experience. Last but not least, we have a bunch of coils here with currents going in the direction of yellow lines, yellow arrows. So using the right hand rule, the 4 fingers should be the yellow arrows. So I'm going to put an arrow, a blue arrow, indicating, actually let me see, indicating the direction of the field. So actually let me change this color to, let's do orange. So orange. So in this case, the magnetic field will point up and to the right. So now let me copy this and paste. Oh, that's not what I want. And paste this. So now right here, the magnetic field will be to the right. And the tip of the arrow is the North Pole, and the other side of the quill is the other side of the quill is the South Pole, and then you have the magnet generated. Now, of course, you can elaborate more on this, and you can add, let's say, you can add shapes. So you can say, let's add this magnetic field here. I can make this, I can use no field, but I can make, let's say, red, and let's make it thick and stuff. So we have a magnetic field going around, and then I can copy and paste, and so we have a magnetic field going from that wire like this. You can, of course, using Word, we can, I wonder if it will look better if I change it to green, or maybe a lighter green, maybe. We'll see. So anyway, so we can do many things with electricity and magnetism. And so forth. You know, the Earth, or planet Earth, has a magnetic field. That's because in the same way that the electric field is curling in this coil, right? Remember, if we go back to Maxwell's equations, the curl of E gives rise to a B, a magnetic field. So the center of the Earth has a molten iron that is rotating, and the rotation of these atoms generate this magnetic field on planet Earth, and we should be very thankful for this magnetic field, because without the magnetic field on the Earth, there wouldn't be life here, because the magnetic field of the Earth is what protects us from very harmful radiations. So this was a brief introduction on circuits and magnetism, pretty much an introduction of electromagnetism.